Venice's aquatic drama, unraveling the complex forces behind extreme sea levels. The idyllic Mediterranean coast, with its picturesque landscapes and historic towns, faces a relentless adversary that often lurks beneath the azure waves: destructive sea storms. These tempestuous events, born of intense cyclones, have far-reaching consequences for the region, including floods, beach erosion, infrastructure damage, and the loss of cultural heritage. The Mediterranean battleground. Researchers have pointed to the shallow northern Adriatic Sea as a hotspot for storm surges in the Mediterranean. Here the storms reach their most devastating levels, driven primarily by a powerful southeasterly wind known as the Sirocco, and also by the northerly to northeasterly katabatic wind known as the Bora wind. This wind phenomenon is often associated with cyclones that originate in the western Mediterranean Sea. The wrath of cyclones. The most extreme storm surge and high wave events in the Mediterranean, recorded in 1966, 1979, and 2018, were all instigated by this synoptic pattern. However, the Adriatic coast isn't the only victim. Other regions, such as the eastern Iberian Peninsula, have witnessed catastrophic events like the 2020 storm named Gloria. This powerful low-pressure system unleashed the most extreme waves and storm surges ever recorded, resulting in floods, coastal infrastructure damage, erosion, and tragically, 13 fatalities. Tropical-like cyclones. The Mediterranean isn't immune to cyclones that exhibit tropical-like characteristics, aptly referred to as medicanes. These storms, while less frequent, can be equally devastating, posing a significant threat to coastal communities. Unseen threats. Meteo-tsunamis. In addition to the menace of cyclone-induced storm surges and high waves, the Mediterranean also contends with meteo-tsunamis, destructive tsunami-like waves triggered by atmospheric disturbances. These waves are particularly menacing in coastal regions along the eastern Adriatic coast and the Balearic Islands. Residents have experienced devastating floods and structural damage due to these meteo-tsunamis.
The classification of the atmospherically forced sea level fluctuation usually is made depending on the scale of the meteorological forcing processes. We can have planetary scale, we have an order of 10,000 kilometers. We can have synoptic scale, which has an order of 1,000 kilometers, and this is characteristic for extratropical cyclones, and also mesoscale phenomena, so a smaller scale, in a range of 10 to 100 kilometers. Those phenomena, they can generate waves and fluctuation of the sea level that can also called meteo-tsunami, and occur when the mesoscale atmospheric pressure recently generate a traveling sea level anomaly, when their speed of propagation approach that of the shallow water barometric waves. It means that when those perturbations propagate over the sea, they can create resonant waves in the sea. They are called meteo-tsunami because they are meteorologically generated long ocean waves, but they are in the tsunami frequency band, so they have a period between few minutes, and a couple of hours. In the Adriatic, meteo-tsunami pose a major hazard, especially on the Earth's eastern Adriatic coast, where they can also have a resonant period close to those of the normal modes of bay arms. It means that they can amplify in a specific location and create devastating waves.
A chilling example of the destructive power of these phenomena occurred in Venice on November 12, 2019. A rare confluence of events, including storm surges induced by Sirocco winds and a meteo-tsunami generated by a fast-moving mesoscale cyclone along the Italian coast, led to a catastrophic flood. The sea level in Venice reached a staggering 1.89 meters above the local high tide average, inundating approximately 90% of the city center. Unraveling the mystery. Despite extensive investigations into the 2019 Venice flood, the specific dynamics of the meteo-tsunami and its contribution to the catastrophe remain elusive. Ongoing research employs numerical models to dissect the event, including the roles of wind and air pressure, the resonance effect, and the interaction between atmospheric perturbations and gravity waves or edge waves along the coastal sea. By comprehending these intricate processes, we hope to improve our ability to predict and mitigate the impact of such destructive events in the future. The Mediterranean may be known for its tranquility, but beneath the surface, it conceals a formidable and ever-present threat. Understanding and preparing for these natural forces are essential steps towards safeguarding the beautiful coastal communities that call this region home. The case of Venice. For more than a century, the picturesque city of Venice has been keeping a vigilant eye on its ever-changing sea levels. The story begins in 1871 when continuous instrumental observations of the sea level were initiated at the Punta della Salute tide gauge. Over the years, these records have provided crucial insights into the complex dance of tides and surges that define Venice's aquatic existence. The Zero Mareografico Punto della Salute, or ZMPS. Venice's sea level records are referenced to mean sea level between 1885 and 1909. This level, known locally as Zero Mareografico Punto della Salute, or ZMPS, serves as a benchmark for understanding the city's unique relationship with the sea. This study delves into Venice's sea level history, spanning an impressive 148 years, from 1872 to 2019. The data include a sequence of water level maxima and minima from the late 1800s to the early 1940s before transitioning to hourly measurements until 2009, when it further refined data collection to 10-minute intervals from 2010 to 2019. However, since October 2020, the installation of mobile barriers, known as the MOs, at the city's 3 inlets has shifted the dynamics, altering the course of future sea level patterns. The complexity of Venice's sea levels. As we unravel the enigma of Venice's sea levels, it becomes apparent that at least 8 distinct factors contribute to the city's daily aquatic drama. First is the astronomical tide. The northern Adriatic Sea experiences a mixed semi-diurnal tide with 8 principal tidal constituents. During peak springs, the tidal range approaches almost 1 meter. Second is storm surge. Synoptic air pressure fluctuations and wind forcing, often driven by the southeasterly wind known as the Sirocco, significantly impact sea levels in Venice. Third are the seiches. Free sea level oscillations in the Adriatic Sea, triggered by previous storm surges, play a role in the sea level equation. These oscillations decay over about 3 days, with the 2 primary modes existing for periods of approximately 21.8 and 10.7 hours, mirroring diurnal and semi-diurnal tidal constituents. Fourth are meteo tsunamis. These large waves, generated by atmospheric pressure disturbances, can occur during fast-moving weather events like thunderstorms and squalls. Coastal resonance amplifies these high-frequency sea level oscillations. Fifth is local wind conditions. Depending on the wind direction, particularly the northeast Bora and southeast Sirocco winds, the sea level difference between the south and north sides of the lagoon can exceed 50 centimeters. Sixth are long-lasting sea level anomalies created by planetary atmospheric waves, or PAW surges, that affect sea levels in the northern Adriatic Sea and contribute to Venice's flood predisposition. Seventh is the interdecadal, interannual, and seasonal sea level variability, or IDAS variability, that arises from atmospheric and oceanic circulation patterns. Factors like lunar precessions and solar activity play roles in this variability. And finally, eighth is relative sea level rise. Over time, climate change and land subsidence have led to a long-term process of sea level rise. Between 1872 and 2000, Venice saw a 31-centimeter relative rise, increasing the frequency of floods. A complex ballet of forces. Each of these contributors manifests sea level variations on the order of tens of centimeters, with storm surge being the most significant, potentially exceeding 1 meter in extreme cases. Notably, factors like river floods, earthquake tsunamis, and waves do not play substantial roles in Venice's sea level variability.
Flooding event that struck Venice and also the northern Adriatic Sea on 12 November 2019, the second Acqua Grande that we experienced in Venice, had a serpent condition seemingly typical of the events causing exceptional high tides, had some very peculiar characteristics that were never observed before, and which was the subject of deep analysis. The peculiarity of this event was that it was made by the concurrency of different forces, different factors. First of all, there was an in-phase timing between the peak of the storm and the astronomical tide. In other occasions, like in the 1960 scene for the strong high water that we have in Venice, the peak of the storm was at lower tide. Now we had that to occur during the peak tide. Moreover, we had a deep low pressure cyclone over the central southern Mediterranean Sea that generates strong scirocco, which is a southeasterly wind, along the Adriatic Sea and pushing waters to the north, so to the Gulf of Venice. Moreover, there was a fast-moving local depression, so a mesoscale cyclone, and also the associated wind perturbation that was traveling in the northwestern direction over the Adriatic Sea, along the Italian coast, and this generated a meteor tsunami. This fast-moving cyclone also generated very strong winds over the lagoon of Venice. The gust peaks around 100 km per hour. And this led a rise in the water levels into the Venice lagoon and also damages to the historic sea. Moreover, we had anomalous high monthly mean sea level in the Adriatic Sea, which was induced by the standing low pressure system over the Mediterranean Sea. And this was associated with large-scale, low-frequency atmospheric dynamics. So that we had that for the whole month of November, we had that the mean sea levels was about 30 centimeters higher than usual.
Recent research on the components that influence sea level in Venice have begun to shed light on the phenomenon and have produced some initial evidence in new approaches. First, researchers have focused on multifaceted drivers. Venice's coastal flooding is influenced by myriad factors, making it a complex puzzle to solve. While storm surges from the northern Adriatic Sea contribute significantly to extreme sea levels, they are just one piece of the puzzle. Other drivers, like tides and long-term meteorological components, play dominant roles in recurrent and even seemingly ordinary floods. Second, researchers have investigated the rising non-tidal contribution. In the past 3 decades, there's been a noticeable upward trend in the non-tidal component of sea levels. This increase can be attributed primarily to changes in interdecadal atmospheric surges and planetary atmospheric waves. Together, these factors create a large-scale dynamical precursor to flooding in Venice. Third is a new appreciation for statistical dependence and the power of copulas in understanding compound events. To understand the statistical interplay among various contributors to sea level extremes and complex compound events, researchers turn to copulas. These mathematical tools account for the statistical dependence between drivers and enhance our understanding of extreme sea levels. This type of analysis uncovers significant correlations among these drivers, impacting the estimation of extreme events. Fourth, researchers are challenging conventional wisdom by revisiting the concept of tide nonlinear resonance, or tide NTR relationships. While traditional tide gauge records suggest an NTR anti-correlation, further investigation is needed. It's essential, especially in the context of climate change, to understand how the drivers of ESLs might evolve differently over time. A global endeavor for coastal resilience. The global scientific community is uniting in a massive effort to comprehend and manage coastal flooding, a formidable threat to vulnerable coastal communities. Venice serves as a vital paradigm in this endeavor, facing both high-frequency nuisance floods and rare extreme events. The methodology applied in this study, applicable not only to Venice but to coastal regions worldwide, provides valuable insights into the physical drivers of extreme sea levels. This knowledge will be pivotal in shaping science-based and sustainable flood management strategies across the globe. As the world grapples with the realities of climate change and rising seas, the lessons learned from Venice's watery struggle offer a glimpse into the future challenges that many coastal communities will face. By understanding the complex interplay of forces shaping extreme sea levels, we take a significant step toward a more resilient, flood-resistant world.
The numerical models that are used to forecast such extreme events need to have a very high resolution, both in the atmosphere and also in the ocean. The next generation modeling effort, therefore, should be focused on kilometer or even sub-kilometer scale atmospheric simulation for describing such a mesoscale cyclone and extreme storm, and also considering those simulations in a climate change perspective. Moreover, one approach for improving forecasts will be to use ensemble of numerical simulation. In this way, we know we have the chance to reproduce the same events with different models. It can occur that all models emphasize the occurrence of severe sea condition and also along the cyclone pattern at the coast. However, due to the rugged and usually complex coastline, extreme sea level are usually localized at a specific coastal site. With the use of a large ensemble of simulation, we can be able to estimate the uncertainty and therefore to understand which area will be more susceptible to extreme events. So the multi-model and multi-physics approach allow us to assess how the uncertainty propagates from the meteorological to the ocean variability and to the subsequent coastal impact. The ensemble mean and standard deviation can be combined together to provide a hazard scenario of the potential impact of extreme events to be used also in flood risk management.